The following video documents a software simulation tool written in C# with visual effects in DirectX that models the beam pattern for phased arrays. This is actually the second of two videos. This one actually shows the modeling using the patch antenna element that the array will be constructed from. The first video modeled the array using isotropic point sources to demonstrate the software and to give 3D models that appear similar to what you'd see in typical phased array text. Okay, so shown here is the phased array panel under construction in the laboratory. It's a 5 patch element array horizontally by 4 element high. It's limited in size because this is a personal project and I wanted to keep the cost down. And I wanted to model the beam pattern that could be expected before actual construction of the array and the receiver to follow. The software is in its first version of construction. It only simulates phased arrays that are flat and not spherical, as you see here. Following versions will handle phased arrays that can be conformally mounted to surfaces that aren't particularly flat in structure. Inter-element spacing is the same between all elements, set at λ/2 in this example. That can be varied in the software, and all elements are exactly the same, so there's no control as yet, which will come in further editions of the software that allow individual excitation of the arrays for or each element for improved performance. Okay, so this is the patch antenna that will be used in the construction. It's an Elcom product, model number HDG2458-LP, 2 bands of operation, 2.4 to 2.5 gigahertz and 4.9 to 5.8 gigahertz bands. It's vertically polarized. Lower band gain is 9 dBi, upper band gain is 11 dBi. Okay, so that's the patch antenna element that will be used, and essentially 2 patch antennas connected with a single end connector in the back. Okay, so design will then have 5 of those horizontally by 4 rows high. Okay. Again, the first video was to show the modeling of the patch or the phased array using isotropic point sources to illustrate the software. So this second video will actually use the real radiation pattern provided by the manufacturer for each of the elements. And this is the radiation pattern from a single element, and it's shown in linear magnitude as opposed to log magnitude, so that as elements are added you can get a better feel for how the beam expands and becomes larger in size, how what's called the array factor forms the pattern as the phased array is continued both vertically and horizontally. So that's the beam pattern of a single element. And you can see it has a 9 dBi gain over the equivalent isotropic point source. There's an isotropic point source where radiation is the same in all directions. And again, here is the pattern of the phased or the patch element that will be used in the actual construction. And by the way, let me show you, there's a screen to one side that isn't shown in the recording continuously that controls the movement of, in the simulation package. This panel controls the yaw, pitch, and roll of the display. So I can show you different orientations of the simulated radiation or antenna pattern. Here's the zoom control along here. This track bar allows control of the element spacing. It's set by default to lambda over 2 or 180 degrees. Here is control of the horizontal beam steering, control of the vertical beam steering, and essentially this group panel here controls a marker for showing angles and gain metrics. Okay, I'm going to add a second patch element. So we now have, zoom out just a bit, we have 2 patch elements horizontally with a lambda over 2 element spacing. Get a view of this side to side. As I add patch elements horizontally, we'll look at the beam width that is achieved. Okay, I'm going to turn this down so you can get a better view of this. So I'm now up to 12 dBi using 2 patch elements horizontally. And so the 3 dB beam width would be roughly 9 dBi. So 31 degrees from center to side. Same for the other side. 9 dBi. 31 degrees, so we're 62 degrees, 3 dB down beam width with 2 patch elements horizontally. Record these numbers as I'm taking them here. Okay, so let me add a third horizontal patch element. See how this looks from side to side. Our view now is we're looking down on the array with the look at. Well, I can actually show you a picture of it here if I can get back to another display. Okay, I'm looking. Let's look in the wrong direction. Oops. Okay, the view you're seeing is essentially this. You're looking down on the patch array with the beam focused out, straight out to down. Okay. Zoom out a bit. Okay, we're now at 3 elements, and our gain is at 13.7 dBi, and from side to side, 3 dB down would be 10.7, roughly there, about 22 degrees from center to side, and same is true for the other side. About 22 degrees. So with 3 horizontal patch elements, our beam width, 3 dB down beam width is 44 degrees. You can see what it looks like at this point. Okay, I'm going to add a 4th patch element. See what that looks like side to side. Again, so we're looking down on the phased array with the front pointed down. Okay, give me we're roughly 15 dBi gain at this point with 4 patch elements horizontally, and our beam angle would be down to 12. Roughly 17 degrees from center to side. Same for the other side. 17 degrees. So we're 34 degrees beam width. That would be the half power point beam width with 4 horizontal elements. So I'm going to add a 5th horizontal element. And you can see what this looks like now. We're looking down on the phased array with the front pointed down. And we're at 16 dBi gain with 5 patch elements horizontally. And so that'd be 16, 3 would be 13. Let's go to 13 on the side here, roughly there. 14 degrees from center to side. And the same is true, 14 degrees from center to side, roughly there. So we're at 28 degree beam width, half power beam width, with 5 horizontal patch elements horizontally. Okay, so let me reset everything here, and let me turn ourselves to the side, and I'm going to start stacking these. I'm going to add a vertical row. Okay, so I now have 2 rows with each 2 vertical rows with each row holding 5 horizontal patch elements. Zoom out a bit, and I'm going to turn this to the side so we can take some measurements. Okay, zoom out just a scamper here. Okay, so I'm looking at, let me go back to the panel showing the phased array. So I'm essentially here looking into the side of the phased array with the beam pointed out to the front. Okay. Okay. The gain at this point is 19 dBi, and beam width is would be 16. 3 dB down point would be 16. So we're 31 degrees from center to side. Same performance for the other side. dB, or so the beam width, 3 dB or half power beam width is 62 degrees. Same performance as adding rows as in adding elements horizontally. So the same performance vertically and horizontally. So I'm going to increase to 3 vertical rows, each row holding 5 horizontal patch elements. Zoom out just a bit. I'm going to rotate this here so you can see what we, whoops. Okay, see what we see here. We are at gain of roughly, let me make sure everything's all lined up properly. Here we are. Okay, 21 dBi gain. This is with 3 vertical rows, and so taking it to 18. With a half power down point. Oh, roughly there. 21 degrees from center to side. Same is true for the other side. So our beam width now is 42 degrees. That's the half power beam width. That's 3 vertical rows. Let me increase this to 4 vertical rows. With each row holding 5 horizontal patch elements. So this is the limit of the proposed design that's being built in the lab. And we have 22 dBi gain with a beam width of 17 degrees from center to side. Same is true for the other side. Okay, 17 degrees. So 34 degrees is the half power beam width vertically, and of course horizontally we have a beam width of 28 degrees. This is 4 vertical rows by 5 horizontal patch elements. Now for symmetry, I'm going to add the 5th row at 5 horizontal elements per row. And again, this is just for symmetry because I'm limited by budget. My physical design will be 5 rows high by 5 elements horizontally per row. Okay, so let's look at the performance here. Again, I'm going to give you rotate this around so you can see it's completely symmetrical, both horizontally and vertically. And we're now up to a gain of 23 dBi. This is a 5 by 5 phased array using patch elements, that piece from LCOM described earlier. And double check the beam width down to 20 roughly, 14 degrees. 14 degrees is the half power beam width here. So our beam width is 28 degrees, half power beam width is 28 degrees both horizontally and vertically. Okay, let me reset everything and bring the axis out just a bit. Okay, so now looking at the beam directly out, we're facing the phased array. Facing the phased array with the beam coming out on the positive z-axis, coming out toward us. Let's see here. Get back to the right panel now. There we go. And for some reason we're not where we need to be on this. Oh, there we are. Need to bring the zoom out just a bit. Okay. Bring the axis up. Okay, so I'm going to sweep the beam now horizontally. To do that, I'm going to turn it down so we can get a better view of this. Turning the beam down 90 degrees. Zooming out. Okay, so I'm looking down on the phased array with the front of the phased array pointed down. I'll swing the beam horizontally. You notice here, not like the isotropic point sources, as we sweep the beam horizontally, beam strength becomes less. So I'm going to keep going to, well, I'll stop there. It appears to be about the half power point. Let me bring it back just for a moment, take another measurement of the peak strength. 23 dBi. Okay, I'm going to sweep this again horizontally. So it looks like if I go down to, okay, roughly there. Oops. Okay. Okay, so if we go to, as in this, unlike the isotropic point source, with the radiation pattern from the patch element, the beam actually reduces in gain as you sweep it from side to side horizontally. And I swept it over to one side, so we're down 3 dB in strength, and we're at an angle of 40 degrees from center. Again, this appears to be the same on both sides. See how the beam becomes smaller? When this is physically finished, what will happen is that each element will not be treated equally when attached to the receiver. There will be control over gain and attenuation from amplifiers and attenuators to ensure that the beam angle or the beam strength as it's swept from side to side remains the same. Okay, let me bring this over. So again, roughly, to bring it down to the about 40 degrees. So horizontally, this design has an 80-degree horizontal beam sweep 40 degrees from side to side, and the beam strength at the limit at each edge is down 3 dB from the center. Okay. Okay. So let's look at the vertical. See how the vertical sweep looks. Okay, I'm going to reset everything here. Point the beam directly out. Okay. Now I'm going to turn it to the side now. Oops. So you can get a better view of the sweep vertically. So here I've got I essentially have the phaser. I'm looking at the side of the phased array. Well, let me just go back to that picture. Okay, we're looking at the side of the phased array with the beam pointed out the front, and I'm going to sweep it up and down. Sweep it up and down. Okay. And let me bring my zoom back out again. Bring my axis up. Okay, I'm going to sweep up. Again, you can see as we sweep up, beam strength becomes less and less. In fact, let me just go back to straight out. See if I can find my markers here. Get those aligned up properly. And so again, I'm at the 23 dBi gain pointed out. As I sweep up, I'm going to take it to the half power, just for grins here. About, oops, let's see. Okay, sweep my angle up. You go a little further with it. And this is the first version of the software, so the markers and such are at a primitive state at this point. So I've got roughly so now down to, okay, roughly 40 degrees from center to top of vertical sweep. Get the same performance if you sweep down, and we'll show that. A little too far with it here. Let's see, bring it up just a tad. So there is roughly 40 degrees. Okay, so with the proposed design, and again I've simulated 5 vertical rows with 5 horizontal patch elements per row. The physical design will actually have 4 rows to keep things within budget here. We're 40 degrees or 80 degrees vertical beam sweep top to bottom, and that would be the beam would be at 3 dB down at the edges from the vertical sweep top to bottom. Horizontally, the same is true, 23 dBi gain, and we'll have an 80 degree sweep, 40 degrees side to side, would give 3 dB down on the edges horizontally. And when the receiver is built and we have control of the gain and attenuation using amplifiers and attenuators for each element, then we can actually control each element and ensure that the strength is the same as the beam is swept from side to side. Again, those features will be added to the next upcoming versions of this simulation package. So let me reset everything here, and let's go back and look at the beam straight out, looking straight on, looking at the face of the phased array. I'm going to sweep the beam from side to side and vertically from side to side, and vertically and horizontally at the same time. Okay, gives you a picture of what this looks like here. Okay, let's look at the effects of changing the inner element spacing. So I'm going to reset everything here, and I'm going to turn the beam to its side. I'm going to try this side. Okay, so I'm now looking at the side of the phased array with the front to the right, and we're at lambda over 2 spacing now. I'm going to take that spacing and slowly decrease it just to see what happens here. And we're at 117 degrees inter-element spacing. As the elements become closer and closer, the beam width becomes larger, and of course your lobes become less in count and smaller in size. And of course, if you take this all the way down to inter-element spacing of 0 degrees, what you essentially have is 25 phased arrays stacked all into one. So you can think of it as a super patch element. And if you turn this out to the front, bring the zoom down, then what you would have is the gain 23 dBi. Okay, so there's your, just to demonstrate the software is working properly. Okay, so let me bring this out to lambda over 2 inter-element spacing. Once again, that's 180 degrees. And now I'm going to move the elements further apart. I'm at 275 degrees space. You can see as they become further apart, the side lobes become larger in size and the beam becomes narrower. Okay. Okay, so this concludes the second video demonstrating this simulation package called the Phased Array Antenna Pattern Simulator. And again, the first version of this it simulates flat phased arrays. Upcoming versions will handle the phase panels that are conformally mounted to shapes that aren't flat, and there will be more control over inter-element spacing and the gain and attenuation of each array to get better simulation of what the antenna pattern looks like before you get into writing firmware and actually building a receiver.